Hi class, welcome back to thermodynamics, and today we're going to learn about the upper limit placed on cycle efficiencies from the second law. So let's get to it. All right, now if you can recall, back a while ago we started looking at thermal efficiencies of cycles. So the thermal efficiency of a cycle was defined as follows. Let me just wake my pen up. There we go. So we had eta is equal to W cycle So eta is equal to W cycle over QH, so heat transfer from the hot reservoir. And we can also write that as equal to QH minus QC over QH, which is the same as 1 minus QC over QH. So here's the thing. We can't have QC be 0. We can't have no heat transfer to the cool reservoir, because that breaks the second law of thermodynamics. Because if we had QC equals 0 there, right, we'd have a single reservoir, which breaks the second law. So no good. Breaks the second law. Okay? And so now there's an upper limit for thermal efficiency, and let's look at that for a sec. So the upper limit for the most efficient heat engine, or the engine cycle, most efficient engine cycle is imposed by the Carnot cycle. So the Carnot cycle is not a real cycle. There is no Carnot engine. It is a theoretical cycle, and it has some of the following properties in that it's a reversible power cycle. So a reversible power cycle. And so it's an idealization, theoretical, not real. And it's made up of 2 isothermal and 2 adiabatic processes. And we're going to dive into the intricacies of the Carnot cycle next lecture. But for now, all we need to know is that this Carnot cycle places the upper limit on our thermal efficiency. So eta max is going to be 1 minus Tc, so the temperature of the cool reservoir over the temperature of the hot reservoir. So remember, keep in mind that these temperatures are on the absolute scale. So if we're dealing with metric, it would be Kelvin. If we're dealing with the imperial system, it would be Rankine. But there are embedded assumptions on this eta max, right? That the cycle is reversible. So otherwise, if the cycle is not reversible, you have to use the ratio of QC over QH here. And so a cycle is reversible when there are no irreversibilities within the system, and also heat transfers between the system and the reservoirs occur reversibly. So that's what makes a system reversible. So when it has the internal and external reversibilities. All right, so coefficient of performance. Now, remember we were dealing with coefficient of performance with refrigeration, with heat pumps. So coefficient of performance can take on positive values, or can take on values greater than 1. Whereas the thermal efficiency has to be less than 1, or between 0 and 100%. So for the coefficient of performance, looking now at beta for refrigeration. So beta is going to be QC, so heat transferred to the cool reservoir, over W cycle, or from the cool reservoir in this case. And that's going to be equal to QC over QH minus QC, right? Or QC over QH minus 1. Okay, so this is refrigeration. And lastly, let's look at heat pump. So that's also going to move from cold to hot. So heat pump coefficient of performance is given by gamma, and that's going to be QH over W cycle. Okay, and so that's going to be the ratio of QH over QH minus QC. Okay, so this is our heat pump. Okay, so there are upper limits also imposed on the coefficients of performance. So the upper limits are going to be the following. So the upper limits and they're also for the reversible cases of these, are going to be given by beta max is equal to TC, absolute scale once again, over TH minus TC, and gamma max is similarly going to be TH over TH minus TC. So in case you need a refresher on what these different cycles look like, I'm just going to sketch them out quickly. So looking at these cycles. All right, so let's start. We'll have our hot reservoir here, and then we'll have a cool reservoir. And this is our system. Okay, so in this case, we're going to be looking at a power cycle. So with a power cycle, we're moving from the hot reservoir, so heat is flowing across this boundary here. So we have QH, okay, into the cool reservoir, and that's QC. And then we're going to have some power output, right? Work done by the system. That's the goal of our power cycle. So W cycle is going to equal QH minus QC. Okay, and this is going to be for our power cycle. Okay, next, let's look at our refrigeration or heat pump cycles. So for those, we have our hot reservoir here and our cool reservoir down here. and then we have our heat pump or our refrigerator. So in this case, the heat flow occurs in the opposite direction. So we're going to have heat moving from the cool reservoir to the warm reservoir. So from QC to QH. So we have our heat flow across the boundary. Let me just delineate my boundary here. There we go. And in order to make that happen, in order to force the heat to flow from the cooler temperature to the higher temperature, you need to put energy in. Okay, so work being done on the system. So W cycle is going to be equal to, once again, QH minus QC. And this is going to be our refrigeration or heat pump cycle. Heat pump cycle. Okay, so for the rest of this lecture, what we're going to do is we're going to look at a couple of problems for your textbook to try out our upper limits on efficiencies imposed by the second law. So let's begin with problem number 510. So the figure below shows two power cycles, denoted 1 and 2, operating in series, together with 3 thermal reservoirs. The energy transferred by heat into cycle 2 is equal in magnitude to the energy transferred by heat into cycle 1. All energy transfers are positive in the direction of the arrows. So first, there are 3 parts to this question. The first part is we're going to determine an expression for the thermal efficiency of an overall cycle consisting of cycles 1 and 2 expressed in terms of their individual thermal efficiencies. So let's just look a little closer at this here. So up top, we have the hot reservoir. Just undo that. There we go. Undo again. So up top, we have the hot reservoir. And so heat is flowing to a cooler reservoir. So the hot reservoir is called T sub H at temperature T sub H. Then there's going to be this intermediate reservoir, which is cooler than the hot reservoir. So, but we're going to call this one T, and there's going to be work out done by the system. Okay, this is a heat pump. So then from the intermediate reservoir, heat is going to be flowing across the boundary to a colder reservoir, T sub C. Okay, and so then there's another work output, W sub 2. So let's start by thinking about the overall cycle here. So our W cycle is going to be equal to, for these 2 cycles in series, it's going to be W sub 1, so the output from the first cycle, plus W sub 2, the output from the second cycle, right? And so we know that W sub 1 is going to be QH minus Q. W sub 2 is going to be Q minus QC. And so this can simplify to QH minus QC. Okay, so our efficiency, so this is for overall. So our efficiency, eta, is going to be equal to W sub 1 plus W sub 2, which is our W cycle, divided by Q sub H. And when you're going around doing these problems with me, feel free to pause at any time and try them out on your own first, and then see how you do. Okay, so this is going to come out to we can simplify this to 1 minus Q sub C over Q sub H. So that is what we would expect. So that's going to be our overall cycle there. So now let's look at cycle 1. Because we want to express these terms in terms of their individual thermal efficiencies. So for the thermal efficiency of cycle 1, I'm going to call that eta sub 1 for cycle 1. And so that's going to equal the work output for cycle 1 divided by QH. So we can rewrite that as 1 minus Q over QH. Because remember, in this case, our cool reservoir is Q. And we can go ahead and solve for QH. So QH is going to be equal to Q divided by 1 minus eta sub 1. Because remember, we want to ultimately express this in terms of their individual thermal efficiencies. So let's look at cycle 2. So cycle 2 so this is going to be, of course, W sub 2. And this time, our hot reservoirs for cycle 2 is given by Q. So this is going to be 1 minus QC, our cool reservoir, over Q. So we can solve for QC. And QC is going to be equal to Q. Oh, and of course, this is our eta sub 2. Times 1 minus eta sub 2. All right, now finally, let's put these pieces together. And our eta is going to equal 1 minus QC over QH. So now let's just plug in our QC, which is Q times 1 minus eta sub 2. Okay. And we're going to divide by, up here, our Q sub H, which is going to be Q over 1 minus eta sub 1. So we're dividing by Q over 1 minus eta sub 1. Okay. And now let's just simplify this a bit. The Q's are going to cancel out. And ultimately, with a little bit of arithmetic, we end up with the eta for our overall cycle expressed in terms of the individual efficiencies is going to be eta sub 1 plus eta sub 2 minus eta sub 1 times eta sub 2. Okay, so that is part A. So let's move on to part B. And for part B, it says, if cycles 1 and 2 are each reversible, use the result from part A to obtain an expression for the thermal efficiency of the overall cycle in terms of the temperatures of the 3 reservoirs. So TH is the hot reservoir, T is the intermediate, and T sub C is the cool reservoir. So reversible, right? So that's ideal in this case. And so we can calculate the efficiencies looking at the ratios of the temperatures. So now we can say that eta sub 1 is going to be equal to 1 minus t over th. Since this is a reversible process, t over th is going to be the same as the ratio of q over qh. And eta sub 2 is going to equal 1 minus tc over t. So using our answer now from part A, we can sub in, and we can say that eta is going to be equal, and I'll just summarize once again. I'll give it a little room. Let's summarize once again. So from before, we had eta is equal to eta sub 1 plus eta sub 2 minus eta sub 1 times eta sub 2. All right, so now let's just plug in. So our overall efficiency is going to be equal to eta sub 1, which was 1 minus t over t sub h, plus eta sub 2, which was 1 minus tc over t, minus eta sub 1 times eta sub 2. So 1 minus t over t sub h times 1 minus t sub c over t. Okay, so now we're just going to have to do a little bit of algebra, a little bit of simplification, and we'll be well on our way. So let's expand out. So eta is going to equal 1 minus t over t sub h plus 1 minus t sub c over t minus 1 plus t over t sub h times tc over t minus t over t sub h minus t sub c over t. Okay, almost there. And so then we end up with eta being equal to 2 minus t over th minus tc over t minus 1 minus t times tc over th times t plus t over th plus tc over t. Now for the fun part, we get to cross some things out. So t over th cancels, tc over t cancels, these t's cancel, and we are left with eta being equal to 1 minus tc over th All right, so once again, we're back to in series. All that matters here is the temperature of the cool reservoir and the temperature of the hot reservoir, right? So at the beginning, we found that overall for the system, for this whole thing, eta is equal to 1 minus QC over QH. However, in this case, now that we're saying this is reversible, eta is going to be equal to 1 minus TC over TH. So it's what you would expect with So lots of math in there. All right. Part C. If cycles 1 and 2 are each reversible and have the same thermal efficiency, obtain an expression for the intermediate temperature T in terms of TH and TC. So in this case, they have the same thermal efficiency. So it's reversible. And eta sub 1 is equal to eta sub 2. Okay. So eta 1 is equal to 1 minus T over TH, which is equal to eta 2, which is 1 minus TC over T. So we know that 1 minus T over TH is equal to 1 minus TC over T. So now we just need to solve for T. Okay, so TH, T over TH is going to equal TC over T. So this brings us to T squared is equal to TC/TH. So T is equal to the square root of TC/TH. And we have a positive root here because it's the absolute temperature scale, and so we don't have negative temperatures. Okay, let's do one more. This is number 43 from chapter 5 in your book. A refrigeration cycle operating between two reservoirs receives energy, QC, from a cold reservoir at TC equals 275 Kelvin and rejects energy, QH, to a hot reservoir at TH is equal to 315 Kelvin. For each of the following cases, determine whether the cycle operates reversibly, operates irreversibly, or is impossible. So the last example, we looked at a power cycle, efficiencies with a power cycle. So for this, we're going to be looking at the efficiency for a refrigeration cycle. So we're going to be looking at beta. So let's just start and determine what our max, our upper limit on our coefficient of refrigeration is, our coefficient of performance for a refrigeration cycle. So beta max is going to be TC over TH minus TC. So we get the maximum coefficient of performance for a reversible refrigeration cycle. And so this is going to be equal to 275 Kelvin divided by TH was 315 minus 275. And this is going to give us a max coefficient of performance of 6.875. Okay, so 6.875 for our beta max. Okay, and so what we're going to be doing with this 6.875 right here is we are going to be comparing our betas for each of the following cases to that beta max. So if the coefficient of performance is equal to beta max, then we have a reversible refrigeration cycle. If the actual beta is less than beta max, we have an irreversible cycle. If the beta is greater than beta max, then that is not possible because it breaks the second law of thermodynamics. So let us begin here. So A, we're given QC is 1,000 kilojoules and W cycle is 80 kilojoules. So now we can calculate QH, which is going to be equal to QC plus W cycle, which is going to be 1,000 plus 80 kilojoules, okay, which is going to be, of course, 1080. Okay, so next, let's just calculate beta. And beta is going to be QC over W cycle. So it's going to be 1,000. So this is going to be 12.5, which is greater than beta max. So our answer here is impossible. So next, we're given a QC of 1,200 kilojoules and a QH of 2,000 kilojoules. So our beta is going to be equal to our 1,200, our QC, divided by our W cycle, which is going to be our QH minus QC. Which is going to give us 1.5, which is less than beta max. So this is going to be irreversible. Okay. Next up, we have part C, where QH is 1575 kilojoules and W cycle is 200 kilojoules. So beta is going to be equal to 1575 minus 200 divided by our W cycle, which is 200, which is going to give us 6.875, which is equal to our beta max. So this one is reversible. Okay, so one more. Part D is our beta, which did not listen to me and make itself, hold on, be Greek. There we are. So our beta, let me draw again, is 6. So that one should be pretty self-explanatory, which is less than beta max, which tells us this is irreversible. All right. So that is all I have for you for this lecture, and I will see you next time when we learn about the Carnot cycle. Take care.